Hi, guys. Okay, so I'm going to walk you through the notes of chapter 7, which is on liquids and phase changes. And in this recording, I will walk you through the phase transitions section. We will talk about the boiling, melting, vaporization, condensation, vapor pressure, temperature, and the intermolecular forces, that is the IMF. We'll also look at the supercooled liquids, superheated liquids, and then the phase diagrams, which is also called the PT diagrams, pressure and temperature diagrams. We will look at the general one. We'll look at the phase diagram of water and carbon dioxide. So first of all, and then also the triple points and the critical temperatures. So first of all, let's look at what causes boiling, or how does boiling occur. So first of all, if you look at this particular container, which is containing water, right? And you are heating this. So here you have the temperature, the red thing, which is showing you the thermometer reading, the amount of heat that is being added into the system. That amount is going to agitate the molecules, cause the collisions in the molecules, and the kinetic energy is going to increase. And with that said, the molecules are going to collide with each other, and then there's going to be a phase change. Now, because the heat is more at the base than it is at the top, so there is a temperature difference. At the bottom, the liquid water begins to convert to gaseous water. So a liquid to gaseous phase change occurs, and that is basically bubbles. The bubbles are the vaporized water, or they are the gaseous water. Okay, so these bubbles have less density, they are light, they move up. So they begin to move up, and they cannot go far, but they stick on the top of the surface, because internally there are intermolecular forces, which are represented as purple lines here. These intermolecular forces are holding these escaping water molecules. So there is hydrogen bonding, there is a dipole moment, there is a London dispersion forces. So all these forces, they form a network of attraction, which prevents the water molecules to escape from the liquid state to a gaseous state. So here we see lots of bubbles on the top form after some time if we continuously provide the heat. Now, as we continuously provide the heat, more and more bubbles reach to the top, and more molecules begin to get agitated, and the collisions increase. And as a result, a time comes when they do escape. They escape, but they don't go far, so they stay on the topmost part of the surface. Now, this top part of the surface is basically just very, it's also, it's up in the atmosphere, it's air. But these wet water molecules, or the water vapors, they do not go very far. They just stick around on the top. They hang in there on the top. So they keep collecting little bit, one by one, they keep collecting. And as you continue to provide heat, as the more and more bubbles are formed, the water is heated up more and more, the temperature rises, and we can see the temperature rising, and more vapors keep collecting at the top. Now, these are called the water vapor, and they have lesser intermolecular forces, so they break up, and they reach, and they stay here. Now, there's something else that is happening. Now, since this is an open system, and in this open system, what happens is that it is being exposed to the outside atmosphere. So what's happening here? Outside atmosphere is nothing but a mixture of gases. So atmospheric pressure is being exerted on these vapors. So what happens now? As the temperature is rising, the more and more bubbles are coming, more and more vapors are collecting on the top, and they are experiencing the weight of the atmospheric pressure also falling on them. So in other words, the outside atmospheric pressure is telling them to go back into the liquid water. But the liquid water is not going to accept them anymore, because now they are in the gaseous state. So this gaseous water vapors just keep collecting at the top, forced by the atmospheric pressure to go down. And as a result, they also start exerting their own atmospheric pressure. And that is called a vapor pressure. So that vapor pressure that is on top of the surface, and this is an open a container. So a time comes when the vapor pressure becomes equal to the atmospheric pressure. When the vapor pressure and the atmospheric pressure become equal, that's when the whole of the liquid begins to boil. So as the temperature increases, the vapor pressure also increases. If you bring the temperature down, the vapor pressure is also going to go down. Okay, so temperature and vapor pressure are directly proportional to each other. So now a time comes when this atmospheric pressure and the vapor pressure become equal. That's when all of the liquid begins to boil. That is called a boiling point, and the temperature is stable. The temperature does not rise in the thermometer. So we see that even though water molecules have hydrogen bonding, dipole-dipole, London dispersion forces, and there's a very strong network of attraction, but as the temperature increases, that collision increases and kinetic energy increases, which breaks that network, and that network becomes weaker. And when the atmospheric pressure becomes equal to the vapor pressure, then that's when the liquid begins to boil. Now keep this in mind, that as the liquid is vaporizing, two things are happening. One is the evaporation is occurring. Yes, the liquid is converting from, the water is converting from the liquid to a gaseous state, but at the same time, condensation is also happening. So the forward direction is of the evaporation, the backward direction is the condensation. So it is, in a way, both these processes are occurring at the same time. And a time comes when both of them become equal. That is the state of equilibrium, when that's when the vapor pressure is attained. So when the rate of evaporation and the rate of condensation becomes equal, at that equilibrium state, the vapor pressure is attained. Okay, so that is the story with boiling. So how the boiling occurs. Now let's look at the heat of vaporization. What is the heat of vaporization? Every substance has a very specific capacity to absorb heat. Okay, so it is the energy required. So heat of vaporization is the enthalpy of vaporization also, and it's represented as delta H vap. The energy required to vaporize 1 mole of liquid at 1 atmospheric pressure. Water, 1 mole of water, which is basically 18 grams of water. The amount of heat that is required to convert that 18 grams of water from the liquid state to a gaseous state is 40.7 kilojoules per mole. That is the enthalpy of vaporization. Now let's look at why we have an ambient temperatures on coastal California. So why does coastal California enjoy the ambient weather, or the weather is always nice? So what happens is that the nights are cooler and the days are warmer. So how does this happen? During the daytime, when the sun is shining, the sand, which is made up of silica, or the land which is made up of silica, it gets hot. And the water should also get hot, but it gets hot slowly. Sand gets heated up quickly, water gets heated up slowly. Okay, so the same amount of heat is going to both, but the heat capacity is different of the sand and the water. So now the land, when it gets heated up, the air, when it gets heated up, the air that's heated up becomes light and it rises up. When the light air rises up, a region of low pressure is created. Now, it is a law of nature that things flow from high pressure to the low pressure. So let's look at what's happening on the ocean. Now, on the ocean, the air is still cool. Why? Because ocean is very slowly absorbing heat. So the water is still very cold. So the air that is above the water is cooler. And cool air is heavy. So heavy and cool air causes a high pressure on the ocean. So now this cool air from the ocean begins to blow towards the land where there is low pressure. So high pressure to low pressure. And on the land, even though the land itself, the surface is very hot, but we have very nice cool winds blowing from the ocean coming towards the land, bringing in the ambient temperature, or a nice cool breeze during the daytime. Okay, so now the ocean, which took very long to heat up, is going to take very long to cool down also. So 18 grams of ocean needed ocean water or water needed 14.7 kilojoules of heat. And think about the massive amount of water that is present in the ocean. So the longer it took for the ocean to get heated up, the longer it's going to take for it to cool down. So now what happens? So during the daytimes, winds blow from high pressure to low pressure. Cooler on the ocean, cool wind blows from the ocean to the land, which is hotter. So the temperature becomes ambient during the daytime. But at nighttime, opposite, land, which got heated up during the daytime quickly, is taking quickly to cool down too. So the land cools quickly. Air over the land is cold and heavy. So therefore, high pressure region. So keep this in mind, heavy, high pressure, lighter, low pressure. So the land, there is heavy land, the air over the land is cold at the nighttime. And so it's a high pressure region. Now, water is still warm. It took very long for the water to cool down now at nighttime. So the air is still going to remain warm. Warm air is light air. So a region of low pressure. Light is low pressure. So the winds blow from the land to the ocean, high pressure to low pressure. So we see that the winds, so when that happens, again, the temperature becomes ambient. Okay, now look at it, what happens on the hills. On the hills, there is less air. So it's low pressure area. But at the sea level, the air is very thick, water vapor in the air, and it's just, people living, civilizations, all those things. So the air is heavy. So high pressure at the sea level. Now, when you're boiling water, you boil water on the sea level. Sea level, the air is very heavy. So the water is going to boil at a temperature higher than 100 degrees Celsius. Because remember, boiling is when the vapor pressure becomes equal to the atmospheric pressure. So the atmospheric pressure is high, so it's going to take longer for the liquids to boil in high pressure areas. On the opposite hand, if there is low pressure, things boil off fast. The boiling point is lower. So the boiling point of water is below 100 degrees Celsius on the hills. So on the hills, the water can boil. You're boiling eggs, or you're trying to make tea or something, the water will boil maybe around 70, 80, degrees Celsius. But on the sea level, you're trying to boil eggs, it may take like 104, 105 degrees Celsius to boil. So like that, okay? So high pressure, boiling point increases, low pressure, boiling point decreases. Now, interpreting graphs. Now, if you just trying to understand a graph, if you have a graph made like this, what does it mean? Okay, so first of all, there are two axes in the graph. You have a vapor pressure graph. Always, everything will have units. So here, the unit is in torr. Temperature, we are reading it is in Celsius. I didn't write this here, but the temperature reading is in Celsius. Now, pressure, vapor pressure in torr, and temperature in Celsius. You see the readings from 0 to +5 to -5. Here, 0 to 5 to 10. So that's the pressure, vapor pressure, and that's the temperature. Now, we are looking at two curves. One is the solid and the liquid curve. So at 0 degrees Celsius, what is happening? Basically, we are trying to freeze water. At 0 degrees centigrade, we say water freezes, but at the same time, water is not 100% as ice. Water is a little bit of liquid also stays. So melting and freezing occur at the same time. Okay, so here we see that. So melting is when the liquid is there, freezing is when the solid is there. So solid curve is represented by this purple color, and the green curve is represented by the liquid vapor pressure, like by the liquid water. So what happens below 0 degrees? We see that the vapor pressure of the solid is lesser than the vapor pressure of the liquid. That is why the water exists more as a solid below 0 degrees Celsius. But once the temperature increases from 0 to even +5, here +5 is still a low temperature. However, the liquid now has a lower vapor pressure, but the solid vapor pressure is high. So that's when so higher vapor pressure means that the solid vapor pressure will be, in other words, it is going to convert into liquid. So the freezing point of water is shown at 0 here. And we see that below 0 degrees, the vapor pressure of solid is lower, vapor pressure of liquid is higher. And with the increase in temperature, the vapor pressure of ice increases. So more than the vapor pressure of the liquid water. That means that the melting occurs. The vapor pressure of ice as a solid, when it becomes equal to the vapor pressure of water as a liquid, that's at 0 degrees Celsius. That's where melting and freezing concurrently occur at 0 degrees. But which phase is going to exist above and below that particular temperature and pressure? That is, we just look at it, the graph, and we can make out that, so which would be, so here liquid will be preferred, and in this case the solid would be preferred, lower vapor pressure, whichever has a lower vapor pressure. Okay, so the lower the vapor pressure, the quickly, that phase is going to form. So liquid is going to form quicker. Here, solid is going to form quicker. Okay, so that's what it means. Now, we see that normal values. Now, there's a term called normal. Normal values are 1 atmospheric pressure. Melting point, freezing point is also considered at 0 degrees Celsius. Boiling point for the water is 100 degrees Celsius. Okay, and this is with respect to water. Now, let's look at the vapor pressure and the intermolecular forces. Okay, so now we are shown these two examples of molecules. One is a diethyl ether, which is a big molecule. If you look at it, it has got C, carbon, hydrogens, 3 hydrogens attached here, then carbon-carbon bond, and 2 hydrogens here, oxygen, an electronegative atom in the middle, and then the 2 carbons and then the hydrogens attached like this on the right-hand side. So now what do we see here? We see that, yes, these carbon-hydrogen bonds are covalent bonds, and they are also, they are covalent bonds, but at the same time, they are non-polar. But in the middle, we see the polarity. So the middle region is a hot region. The outer regions are the cold regions. And this is a big molecule. 74.12 grams per mole is a very big weight. Now you look at on the other hand, look at water, very small molecule in comparison. Okay, it has got oxygen also in the middle, just like the diethyl ether has oxygen in the middle, but on the 2 sides are the hydrogens. So it's a really small molecular, molar mass 18 grams per mole. However, look at the boiling point of water. Boiling point, even though it's water, even though it's a small molecule, has a very high boiling point, 100 degrees Celsius. Diethyl ether, on the other hand, is comparatively a very big molecule spread out, but its boiling point is very low. It evaporates faster. So why is it that the water, being a very small molecule, does not evaporate faster, but the diethyl ether, being a big molecule, it evaporates faster? So in other words, it's easy for the diethyl ether to go from a liquid state to a gaseous or a vaporized state. But water would need a lot of heat to convert from a liquid to a gaseous state or vaporized state. And at 1 atmospheric pressure, these are their boiling points. So what is happening? The reason is the intermolecular forces. So we see in water, there is hydrogen bonding. Anytime the water, hydrogen is attached to oxygen, hydrogen bonding is going to occur. So OH bonds, hydrogen bonding. This oxygen lends its lone pairs to the hydrogen of the neighboring atom, a neighboring molecule. Okay, so this oxygen will have a delta negative charge. This hydrogen has a delta positive charge. This hydrogen has a delta positive charge. So what happens is that these water molecules will have a dipole in them. They will have hydrogen molecules, hydrogen bonding, right? Oxygen has a lone pair. So yeah, this is a polar molecule, and they also have the London dispersion forces. London dispersion forces are present in all the molecules. Okay, now what happens here in the case of diethyl ether? There is no hydrogen bonding. Yes, there is oxygen, but there's lone pair on the oxygen, but this oxygen is connected to carbons and not to hydrogen. Hydrogen bonding only occurs if oxygen is there with the hydrogen atom. So OH bond is not here. It's only the OC bond. So no hydrogen bonding. And this is fine. This is a symmetrical molecule. This is symmetrical molecule. And yes, there is a lone pair here. There's a more electronegative oxygen here. So yeah, the polarity is in the middle. So there is some dipole-dipole, but it's a small dipole-dipole in this molecule. Oxygen has a bigger dipole-dipole. Okay, it's a small dipole-dipole, and London dispersion is present in both. But there are more intermolecular forces present in water, which means that there are more, what are these called? The more network. Her network is stronger in water. So that is why then we need more heat to break that bond. Okay, but in diethyl ether, it is less. So in general, we see that if you increase the molecular weight, the intermolecular forces are going to increase. Generally, if nothing else is there, at least the London dispersion forces are going to increase. And when the London dispersion forces or the intermolecular forces are more, it will take longer for the liquid to boil. So that means the vapor pressure is going to remain lower. Right? It won't evaporate easily. So vapor pressure is lower. So in that case, I think this is the boiling point. Well, I mean, I don't get that. Why did I put this boiling point lower? But you will need more heat to boil the liquid. Okay. So the vapor pressure, in order to increase the vapor pressure, you need to continue to provide more heat. So the boiling point also increases. Okay. So in this case, it should be opposite. Vapor pressure should be high, then the boiling point should be high for heavy liquids, okay? Now, the vapor pressure and the temperature, as we talked about, go hand in hand. The more heat you provide, then that's when the vapor pressure increases. The more heat you take back, then the vapor pressure also decreases. Now, this is a very interesting graph, and you can interpret also from this graph. The only problem here is that this is not a linear graph, it's curved. So you cannot make predictions. However, we should be able to still, based on what we see on the curve, we should still be able to, calculate or determine the unknown. So here is this three curves. One is of ether, one is the alcohol, and one is the water. So the green is for water, alcohol is the blue, and the purple is for ether. Now, torr. Remember 760 torr. 760 torr is the normal pressure for us, atmospheric pressure, okay? Now, from 0 to 30, so all this is the readings in degrees Celsius. So at 760 torr, the blue line here, if you extrapolate, you see that the ether would boil somewhere, above 30, maybe about 34 degrees Celsius. Okay, here above 70, this is falling at the we are determining the boiling point. Always look at the normal atmospheric pressure. So 760 torr is the normal atmospheric pressure. So now here what's happening, 74.8 degrees Celsius is the ethyl alcohol. And for water, it's 100 degrees Celsius. Okay, so now you can, so these are the curves you can make out. Now here, if someone asks you, find out at what temperature would be, at what pressure and what temperature, what, ethers, you can find out, you can look at that, and at certain temperature, what would be the boiling point, or, those things, you can determine that. Now, Clausius-Clapeyron equation, problem with this type of thing is because it's curved, so it's not linear, so it's hard to make predictions. But Clausius-Clapeyron equation has studied the vapor pressure and the temperature, and here he have brought in a linear equation, a representation of the same thing. So how has he done this? So here is your equation of a linear equation. So y is equal to mx plus b. So what is y? Y is the natural log of vapor pressure, is equal to negative delta H, that is the heat of vaporization, over R. This is the slope, which is m, times the value of x, which is inverse of the temperature, 1 over T, plus b, plus c. plus C is the C stands for the y-intercept. So B, that is B. So here is a y is equal to mx plus B. So now enthalpy of vaporization, delta H vap. Gas constant, the value of gas constant is different. It's 8.3145 joules per K mole. 8.3145 joules per K mole. Temperature in Kelvin. C is a constant. It is a constant. It is a characteristic of liquids. Okay. It is a characteristic of liquids, and it is depending what the liquid is. What the liquid is, it has a value based on that. So remember, every substances are going to absorb their own amount of heat, and based on that, their boiling points and melting points are determined. So it's the nature of the substance. So now Clausius-Catalan equation has because of that equation, we were able to see a linear line on the graphs. So we see the natural log of vapor pressure and the inverse of the temperature. When we do that, we see the slope is delta H vap over R. And if you look at it, ethanol, water, and ether, all of them, have been seen in a straight line. Okay. Now, there is heating and cooling curves also. Now, what is the heating and the cooling curve? So here we see that this is the amount of heat that is added, that is on the X slope, the amount of change in the temperature, or the temperature basically is in degrees Celsius on the Y slope. Now, pay attention to this. Now, here we see 0 degree and here. So this is for water. So here's the ice, then it stays for some time, absorbs some heat, converts to water, stays water sometimes, absorbs heat, begins to absorb heat, and then after that converts to vapor. So these slopes are the states of the matter. In this case, it's water. So it's ice here, or a solid state here. This is the water state, the liquid state, and this is the gaseous state. Okay, so that's one piece. Now, what are these plateaus? Plateaus are the amount of heat that is absorbed. So in this case, this is the heat of fusion. Heat of fusion is the heat that is needed to convert the solid to a liquid state. Now, what is this? Delta H vap here. This is a vaporization, the heat of vaporization. That is the amount of heat that is needed to convert the liquid to a gaseous state or vaporized state. Okay, so here, when the substances begin to start melting, the red dot, this is when they start melting. This is when the melting stops. Similarly here, this is where the liquid begins to boil, and this is where it stops boiling. So what's happening here? This state is actually a state of equilibrium. Fine, the heat is being absorbed, but the ice begins to melt. So a solid ice begins to convert to a liquid water. Right? This state, the heat of fusion. And we just need a small amount of ice to convert the solid ice to solid water to a liquid water. So just a small amount is needed. However, the melting and the freezing are occurring at the same time. So it's at an equilibrium state. So it's simultaneously they're going. So if you remove the heat, yes, it can go back to the solid state. Okay, so here the heating, the melting, and the freezing occurs. It starts, here it ends. When all of the ice has melted, then it becomes water. Now, if you continue to provide some heat to it, then the heating will continue. The water will continue to absorb heat. It will continue to absorb heat. It continues to absorb heat. And a time comes when sufficient heat is being absorbed, and it is, at our normal atmospheric pressure, the pressure is not changing. So it has absorbed a certain amount of heat. And that's when the liquid begins to boil. So it's converting from a liquid to a gas state. So here we see is the water in a liquid state and the water in the gas state coexisting. So that's when the liquid is pretty much boiling. That is delta H vap. So all of the liquid only boils when all of the liquid has converted to the gaseous state, and that happens when it has absorbed a very specific amount of heat. So we see that the heating and the cooling exist side by side. melting and the freezing exist side by side. Here, boiling and, vaporization and, condensation occur side by side. So that is why water vapors are wet, right? So condensation. So when all of the liquid has boiled, has an exact amount of that heat has been absorbed, all the liquid has finished, converting to the gaseous state, that's when the plateau ends and the new phase begins. So this is how you interpret. Now, the kind of questions that can be asked on the exam is like, identify the boiling point, identify the melting point, how much is the heat of vaporization, how much is the heat of fusion. So pay attention to one thing. This plateau is small, but this plateau is very big. Okay, why? And there is always, depending upon what the liquid is, right, the amount of heat of fusion and the amount of heat of vaporization, it's always in some multiple. The heat of vaporization is always going to be more than the heat of fusion, that's for sure. Okay, but how much it is, it depends on the substance. So for the water, it is 7 times more heat to vaporize the liquid water than to melt ice. So if you are putting this, if this is 2x, if this is 1x, this becomes about 7x. Not exactly 7x, but about 7x, 7 times more. Okay, so the boiling point plateau, when you make these, just pay attention to these markings here, just make them 7 markings more. So if this is 1 marking, this would be 7 more. Okay, now here, the heat of fusion, what is that? How you define it? It is the amount of heat required to convert the solid at its melting point into a liquid at constant temperature. So the temperature doesn't change. If you look at it here, melting, when a solid is melting, the temperature is not changing. Similarly, when a substance is boiling, the temperature does not change. Although it reaches that temperature, 100, and it remains at 100, the thermometer reading doesn't move, right, till all of the water has boiled off. Okay. Now, vaporization is the amount of heat required to convert liquid at its boiling point to the gaseous or the vapors at the constant temperature. And what is molar heat capacity? It is the heat required to raise the temperature of 1 mole of substance by 1 degree Celsius. So here we are looking at the moles. Now, here's some examples. Heat of fusion is converting from solid to liquid. Heat of vaporization is converting liquid to gas. Now, here you see a substance, for example, water, chloroform, and sodium chloride, 3 different substances. The melting point of water is given 0 degrees Celsius. The melting point of chloroform, CHCl3, is negative 64 degrees Celsius, which means, it will evaporate very fast at room temperature. So anyway, so here comes the sodium chloride, which is solid, and its melting point is so high, you really have to heat it like very high, 800 degrees Celsius. That's a lot. Okay, so this means that water will absorb a little bit of the heat to convert from a solid like the ice state, and that is equal to 6 kilojoules per mole. Chloroform needs 9 kilojoules per mole, but sodium chloride needs a lot, 30 kilojoules per mole. But look at this now. Water, 6 times 7 roughly is about 40 kilojoules per mole. So the boiling point of water is 100, chloroform 61.7, and sodium chloride is 1413 degrees Celsius. So here you have the water, the boiling point is 100, and its heat of vaporization is 7 times more, so it's 40 kilojoules per mole, in that range roughly. Chloroform is about 4 times more, so 9 fours are 36, so about 31 kilojoules per mole, so it's on roughly. Sodium chloride is 6 times more. So in any case, the heat of vaporization is always more, okay, is higher. Okay, now what else do we see here? On the graph, if you are not given sodium chloride, if you're not given water, but you're given some other substance, so just make sure that this is, when you read what is the heat of fusion and the heat of vaporization, just make this graph, this plateau, that many times more than the heat of fusion, depending upon what material you are looking at. Okay, now we are looking at the next is the concept of supercooled liquids. What are supercooled liquids? Supercooled liquids are like cool below like even their freezing point. Okay, so in other words, water will not convert into ice. This is super cooled water at 0 degrees centigrade. Water does not convert to ice. A liquid does not convert to a solid state at its freezing point. That is a super cooled liquid. It remains liquid at that temperature. Liquid state exists as a liquid far below its freezing point. Now, supercooled liquids will only convert to solid in the presence of seed crystals. And the seed crystals, they provide the site for nucleation. So what does this mean? Now, here, that means very pure liquids, very pure liquids. And these pure liquids are like, for example, there are no vapors, no viruses, no bacteria, no air also, and no like any kind of any kind of impurity. So it's a 100% pure liquid, right? And so this liquid does not have any impurity. So we do need little bit of some kind of impurity, some base, some site we need for the crystals to form. What is solid? Ice, formation of solid. Ice, for that's ice, right? Ice is basically solid. So the solid develops on those sites. You know, those are the sites for the nucleation, means development, where the crystallization starts. Okay, so you must have seen, like, if you take water and you add sugar into it, right? The sugar dissolves and it's all inside. But you can, if you put like something into it, like a little, maybe a toothpick, or maybe if you prick that liquid and you're cooling it, and let's say if it doesn't solidify, if you prick it, immediately the crystals form. Or if you put a thread in it, immediately the crystals begin to form on that. So that site is over which the crystals form. So if the water is not freezing at all, so if you add a little bit of ice, a teeny bit of ice into it, immediately the whole of the water is going to freeze and make the ice. So immediately the liquid begins to convert into solid. And so this is a process of crystallization. Anyways, the supercooled liquids occurs when the liquids are very, very pure. They are free of the nucleation sites. There are no bacteria, no viruses, nothing, no ions, nothing. So we see that the waters freezes at 0 degrees Celsius at 1 atmospheric pressure, but the supercooled liquid, which is a water, can remain as water at 1 atmospheric pressure, even at negative 48.3 degrees Celsius. So supercooled water, it can exist there, provided the water is extremely cold, like cold, of course, but at the same time, pure and free of any nucleation site. So where do you find the supercooled water? You find the supercooled water in clouds. And this is the reason why. In cloud, there is this pure 100% supercooled water, like far above the earth. And when the clouds, when these above these clouds, when you have the airplane flying, and here you have very clean supercooled water existing like little vapors, but water, and here comes the airplane, and immediately the water is going to make ice, and that happens on the airplanes, on the the glass, so on immediately. So icing happens. So what happens is that now the airplanes, obviously it affects them. So the aircrafts have the de-icing surface, or a paint is such that the ice may not form on the aircrafts. Okay, now in the animals, right, on the polar regions, they have antifreeze proteins, right? And these proteins, they help to prevent the water from freezing far below the freezing point in the polar regions. So the animals, or these animals, can survive, like polar bears or penguins. These guys can survive like sub-zero temperatures, and the water inside their body doesn't freeze because of the presence of these anti-freezing these proteins. Now, if we want to preserve livers, right, or any, like, want to preserve livers, and you don't want the liver, you don't, obviously, if you freeze them in ice, maybe they go bad. So how do you do that? Super cooled water is used. So far below, what it can remain as water till negative 48 degrees Celsius. Okay, negative. So that's the thing. Now, water itself can be made it into a glass. How? If water is cooled at the rate of 10 to the power 6 K per Celsius per second. So the site nucleation is avoided and the water can be made into a glass. So the speed with which it is cooled is also, factors in that. So to avoid the nucleation. Okay. Now that was about the super cooled liquids. Now comes the superheated liquids. Now water, sometimes when you heat, sometimes oil also, when you heat it, and if it's not disturbed, then it can even stay hot beyond 100 degrees Celsius at 1 degree Celsius. So at 1 atmospheric pressure. So in this scenario, what do we see? We see that the liquid water will not convert to gas. In other words, water will not boil. So water does not turn into vapor. And also, at very high pressures, the water can boil above 100 degrees Celsius all the way till 374 degrees Celsius. But a superheated water will lose its property. It is not viscous. It does not form beads. It does not have surface tension. There is no, hydrogen bonding is not there in a superheated water. And there is only the heat capacity of the water has increased. That is why it is staying in a liquid state far above 100 degrees Celsius, all the way till 374. Okay. And again, if it only happens if the water is very, very, very pure, 100% pure water with no site nucleation. Okay. Now comes the phase diagrams. Now these phase diagrams are going to be obviously on the test. So you have to understand these phase diagrams. Phase diagrams are also called a PT diagram. So there are parts to it. So first of all, let's look at it. On one end is the pressure. Okay, one end, that is the y-axis is the pressure, and generally pressure is an ATM, but the book is talking about torr, book is talking about kilopascals, whatever works. Okay, so that's the pressure in one ATM, in ATMs, and here is the temperature generally in degrees Celsius. So the x-axis temperature, y-axis is the pressure. That's one piece. Next thing is there are three parts in the phase diagrams, and that part is, one part is the solid, S stands for solid, L stands for liquid, and we have the G, which stands for gas. So we are showing these three, in these three quadrants, we're showing these three sections, we are showing the three states. Now when you move from a solid to a liquid state, when you move from a solid to a gaseous state, let's look at that first, solid to a gaseous state. When you heat the solid, it converts to a gas, and that process is called sublimation. So as you increase the solid, temperature of a solid, it begins to convert to a gas. So this line is meaning the sublimation. Okay. Next is, what is this? This is melting. Melting is when the solid is heated and it converts to a liquid. So this line is shown, is the melting line. Next is this line, this purple line in which the liquid phase is being converted to a gaseous state is represented as vaporization. Okay, so the heat, so sublimation, melting, and vaporization on the purple line. Next thing is, if you look at this red line, this red dot and this red dot, what is this? This red dot is T3. T3 is the temperature. This is the triple point. This is the triple point, and P3 is also the triple pressure. So triple point is what? Triple point is where the solid, liquid, and the gases coexist. Right at that temperature and pressure, the three states of matter can coexist. Just like you've seen, melting and boiling. So vaporization and condensation occur at the same time. Melting and freezing occur at the same time, right? So that coexist. So same is the case, it is possible to see solid, liquid, and gas exist at a particular temperature and a particular pressure, and that is called the triple point. On the other hand, you see TC. What is TC? Now TC stands for critical temperature, and of course this occurs at a certain pressure. At a critical pressure and a critical temperature, we see the liquid is going to convert to the SCF, which is the supercritical fluid. Supercritical fluid and then gas also. So it contains the properties of the liquids and the gases. But this occurs when the temperature is exactly at that particular temperature called the critical temperature. Okay, so we see these three things we saw on a vapor pressure diagram: sublimation, melting, and vaporization. You should know which lines represent what. Next thing, you should know where is that triple point. So you should either, sometimes in the books it is as shown as TP, or it is shown as T3 or P3. Okay, and this is right at that one point on that diagram, solid, liquid, and gases exist. Okay, and this always at a very specific pressure and temperature and very characteristic of a substance. Now, critical point, this is where the supercritical fluids are formed. Supercritical fluids, SCF, they have the properties of gases and the liquids. Now, very interesting. What does that mean? They dissolve other substances, like in liquids, just like the liquids, they dissolve substances, right? Solubilizing. So just like the liquids, they dissolve or they solubilize. Similarly, supercritical fluids also, they dissolve things, but they are lighter. So they are lighter than the liquids and have low density. So liquids less dense, and they effuse like gases. So they can, like gases spread out. So similarly, these supercritical fluids can also spread out just like the gases. So the only thing is that supercritical fluids only exist at very high pressure and a very high temperature. So obviously, far beyond our normal, conditions. So we shouldn't, very scary kind of phenomena here, but extremely high pressure and extremely high temperature, then it is possible to attain supercritical fluids. Okay, so that's one thing. So then now let's look at these phase diagram of water. Okay, now phase diagram of water. So something you have to keep things in mind about this curve. Now for the water, this curve is negative. Okay, it's not all the time like, so for water, this is a negative curve. The slope is negative. Okay, so we see here back sublimation curve. This is the melting, and that's the boiling. Melting is going from a solid to a liquid state. Boiling is going from a liquid to a gaseous state. This is for the solid. This whole area belongs to solid. This whole area belongs to liquid, and this whole area is the gaseous state. Okay, now point to note. Here, 1 atmosphere is our normal atmospheric pressure. Okay, 1 atmospheric pressure is our normal atmospheric pressure. 1 atmospheric pressure and the temperature 0 degrees Celsius, this is normal, right? So the triple point for water is lower than 1 atmospheric pressure right here. So the P3, the triple point, is lower than the atmospheric pressure, right? And so with that said, we see also that the temperature of the P3, the triple point, is a little bit higher than 0 degrees Celsius. Okay, so the kind of questions that can be identify the freezing point. So freezing point is when a substance converts from a liquid to a solid state. So where is that happening? Freezing point or a melting point, where is that happening? So here is this liquid, here is a solid, so it has to be somewhere in this line. And normally, if they're just saying identify the freezing point or melting point, you have to look at wherever there is 1 atmospheric pressure and whatever temperature it falls. So in this case, it's water, yeah, so it's 0 degrees Celsius. Now, if the question is asking identify the boiling point, so you should know boiling point is converting from liquid to a gas state. So where does that come? Always boiling point, melting point always have to be at 1 atm. So 1 atm boiling point with liquid, so just come down and note down the temperature. So in this case, it is 100 degrees Celsius, and that is water. So this is something you have to keep in mind, that 1 atm is our normal boiling point, normal melting point, right? Normal freezing point, those things. So next, they can also ask you, now look at this, at a lower pressure and a lower temperature. Now, lower temperature in this case is 0. Right? 0. 0 degrees Celsius and lower than 0 degrees Celsius and lower pressure. Now, where do you find that? Where do you find lower temperature and lower pressure? Up on the hills, right? On the Himalayas, there are places like Nepal, Bhutan, Tibet, here people wash clothes just like, maybe people don't have the washing machines. They can wash their clothes in hot water, but how do they dry them? The sun hardly comes out. And let's say they don't have the washing machine and the drying machine. Then what do? They take their wet clothes and they leave them out in the out on their patios or out in the open. And that's where the water, which is actually, the temperatures are sub-zero. So the water is not in a liquid state. The water is now in the ice state. And so at that temperature, which is lower than 0, and the pressure is also lower, a time comes when that liquid, when the water, solidified water, begins to convert into gas. So in other words, vaporizes. In other words, the iced water through the process of sublimation is lost as, vaporized water, and that's how the clothes begin to dry. So lower temperature, lower pressure, lower temperature is below 0 degrees Celsius, lower pressure is below 1 atm. So in this case, we see that the liquid water remains in a solidified state, and in a solidified state, through the process of sublimation, it converts to vapors. Okay, so this type of question can be asked again. Tell at what temperature and what pressure, what kind of state is going to exist at a certain temperature and pressure. Tell whether a substance would be what is the process going to be? Sublimation, melting, boiling, those things. This type of questions can be asked. Okay. Next is, and this is the last one, we are looking at a phase diagram of carbon dioxide. Now, here is a difference between this phase diagram and the previous one, and that is that this line, the SL line, is a positive slope. For carbon dioxide, this is a positive slope. That is the line between the solid and the liquid. Okay. Now, here, pay attention to this. Where is the triple point? The triple point here is above the normal 1 atm. So for the carbon dioxide, the triple point is above 1 atm. Okay. But for us, so here is this carbon dioxide solid, and this is the gas, that's the liquid, right? This is the triple point, and that occurs at a certain pressure, and which is I don't know what pressure is that. I don't know why it says 5.3. Maybe I'm missing something. But anyways, the temperature is negative 56.6 degrees Celsius. So the carbon dioxide can exist as a solid, dry ice, as a gaseous carbon dioxide, and as a liquid carbon dioxide at negative 56.6 degrees Celsius. This is what it means, the triple point. Okay. And again, it's only at a certain pressure. But 1 atmospheric pressure, so in other words, at a very high pressure, you look at this, 1 atm, go above 1 atm at a higher pressure, the carbon dioxide can exist as solid, liquid, and gas. But the temperature is still very low, negative 56.6. So very low temperature and extremely high pressure, it's possible to get the 3 states of carbon dioxide to coexist at that particular point. Okay. But the moment you increase the temperature further and further and further, so this dry ice, solid, right, at a very high pressure. So you can see the solid dry ice. Here's our normal temperature is 25 degrees Celsius. That's our normal. So in our normal temperature and 1 atmosphere, this is our situation. We see carbon dioxide in the gaseous form. And in order to convert carbon dioxide at this stage to a solid carbon dioxide or a dry ice, we need to increase the pressure. So you will keep on increasing the pressure. Now, a time comes when, you will reach, like, this is solid, it bypasses that, and it all is going to convert to a solid. Okay. So solid carbon dioxide is called dry ice. It vaporizes. And as the temperature is increasing, again, as the pressure goes down and the temperature increases, then it begins to convert to a gas, or it begins to melt. Very quickly it does that. So sublimation for carbon dioxide dry ice is very fast. Immediately it vanishes. But here's the thing. This is a critical point for carbon dioxide, which means where the liquid carbon dioxide right here and the gaseous carbon dioxide, right? And that is, they kind of coexist. And that temperature is slightly above our temperature, normal temperature, that is at 31 degrees Celsius, but the pressure is extremely high. So what happens is that at a pressure of 72.8, now inside the capsules of fire extinguishers, we have liquid carbon dioxide. So liquid carbon dioxide at a pressure of 72.8 is like, it's extremely pressurized at that temperature, right? Now, what happens is the moment you open that, immediately the moment you open that plug, right, that fire extinguisher, you remove that little ring plug, you unplug it, liquid carbon dioxide, which is already under a very high pressure, now the pressure is released. Lower pressure, you brought the pressure down. As the pressure goes down, the liquid carbon dioxide immediately converts to the gas, and it helps to extinguish the fire. So fire extinguisher, we already talked about it. The liquid carbon dioxide will convert to a gas carbon dioxide when the pressure is released or lowered. Okay, so on the PT diagrams, again, you will be asked either, find the boiling point, find the melting point, find the, what state it is, find the critical point temperature or critical point and triple point of a substance. So basically those things. Okay. So if you have any questions, you can always ask me. These notes are available in the modules, and so we will just do the liquid and the phase changing. For now, we are leaving the solids, and you can also leave out doing these problems 10.7, 10.8, 10.9, and 10.10 from the Open Stax chemistry book. Okay, thank you so much. Take care. Bye-bye.